Hello everyone, I'm Sunggun Kim, a PhD student of Texas A&M University. In this video, I'm going to talk about execution stage of y86-64 sequential processor design. Okay, let's take a look at the diagram of execution stage over here. So to be simple, ALU so execution stage takes two operands, let's say operand 1 and operand 2, operand 1 and operand 2, and then it does the given function from this ALU function. And then its output of this operation will be stored in val E, and some condition code will be stored in condition CC module. So again, it performs this ALU performs the operations, and we have four operations: add, sub, AND, and XOR. As you can see in the function code table, so there are four operations: add, sub, AND, and XOR. And it has three inputs: ALU fun, A, and B. And there are four possible inputs to ALU fun from 0, 1, 2, 3 from ALU fun module. And then the ALU for ALU A operand 1. So there are four possible inputs from ALU A module: val C, val B, positive 8, negative 8, or Z, which means just unknown value. And then for the input ALU B or operand 2, there are three possible inputs from ALU B. So val B, 0, and Z value, like unknown value. So the result of this computation will be out through this val E, and it will also output three condition codes: zero flag, sign flag, and overflow flag. And in the next slides, we will see how we generate these condition flags in the ALU, and then we will talk about in which condition we will store this condition code to the CC. And then next we'll talk about condition module, which will be used by jump and conditional move instruction. Okay, so as far as these 3 bits condition code, let's take t equals to a plus b as an operation in the ALU. And then for zero flag, it is simple. So we set this flag when t equals to 0. And for the sign flag, we set this bit when t is less than 0. And for the overflow bit, it is a little tricky. So the overflow flag indicates that the most recent operation caused a 2's complement overflow. So I'm not going to talk about details of this 2's complement overflow, but you can just implement this condition, this equation in your gate logic. Okay, so then let's talk about CC module. So it will store the last condition code, and it is controlled by setCC over here. Okay, so setCC will output 1-bit signal to update the CC value if the current I code is 6. So which means if I code is 6, then this is one of the 4 instructions: add, sub, AND, or XOR instruction. So for other instructions like jump or move instruction, for example, so this set CC module will just output 0 value, then CC module is not going to store the current condition code from the ALU. We will just keep the previous condition code. Yeah, and then again, so this condition code is going to the condition cond module, and then this cond module will output 1-bit signal, and this signal will be used by jump instruction in PC update stage and conditional move instruction in the write back stage. So let's take a look at the condition mode in more detail. So it takes iFun and CC as an input to the condition module, and it generates 1-bit signal as an output. And it actually evaluate the jump condition if it is jump instruction, or move condition if it is move instruction. So for example, for jump instruction, since it is unconditional jump, so it outputs 1. It does not see any conditional bit, condition code. It just unconditionally outputs signal 1 to jump to the label. But if it is conditional jump, like jump less than 0, jump equals to 0, then it will output if 0 flag is set. It will send 1 if 0 flag is set. Or if jump not equals to instruction is current instruction, then it will return the outcome, like result of this condition, right? So if current outcome of ALU is not 0, which indicates not 0 flag, not 0 flag here, then we need to jump to this label. Okay, and again, if it is jump greater than 0, then to see if the outcome of output of ALU module, like val E is greater than 0, to check this condition is true, we use this jump condition. So if this, we will output a signal 1 if this condition is true. And then we do the same way for the later jump instruction. And also same way, if current instruction is move instruction, then it will output signal 1 for move E instruction, C move E instruction if this move condition is true. Okay, so then you can implement so this condition cond module based on these 2 tables. Okay, then let's put everything into this table, the right hand side. So it has a control signals ALU A, ALU B, and ALU fun, which are generating the input to the ALU, and we have a set CC module that generates input to CC module, either 1 or 0, and we have a cond module which generates output to the output for the jump or conditional move instruction. So based on the transformed computation tables for execute stage, we can fill up the table on the right hand side. Okay, and let's take 3 examples in the table in the instruction, like RM instruction, OPQ instruction, and jump instruction. So for RM move instruction, it writes value of register RA to the memory address D plus RB. So in execute stage, we need to calculate effective address, which is val B plus val C. Okay, val B stores a register value of RB, val C stores the displacement in the instruction. Okay. And then for this computation, we need to select val C by ALU A, val B by ALU B, and then ALU function code would be 0 because we need addition. And then since it is not the logical or arithmetic instruction, we don't set current control condition code to the CC module. And then we don't care about output of condition cond module because it's not it is not a jump instruction. Okay, the next instruction is OPQ instruction, which operates val B op val A. So here OP code will be given in the function code in the instruction. Okay, so then for this instruction, we need to select val A from ALU A module and val B from ALU B module, and then we just select I function in the instruction register, and then we set CC output of CC set CC module because it is either arithmetic or logical instruction. But again, we don't care about output of cond module since it is just arithmetic. It's not a jump instruction. Okay, then last example is jump instruction here, and then in the execute stage, it doesn't actually execute anything, any operation given in the ALU function code, but it is just updating. It just outputs conditional signal cond signal from the cond module by taking the current condition code and instruction function. So then for input to ALU, actually we don't care about the input from ALU input by ALU A. Also, we don't care the input generated by ALU B, and also we just don't just put any special operation, and default, in this case, default operation is 0 all the time. So I put 0 here, and then since it's not logical or arithmetic operation, so arithmetic instruction, so we don't want to store current condition code. And but we need to generate correct cond signal from the cond module. So this signal will be used in the PC update stage when we update PC value. Okay, that's it for execution stage. We actually went over inputs and outputs for each modules in the execution stage, and then we talked about how to set or reset 3-bit conditional code, and then when to store this conditional code to the CC module, and then based on the current CC module with instruction function, we generate cond signal, the conditional signal from the cond module. And then this signal signal is the result of resolution of condition of each jump or C move instruction. And then we put all this information into one table so that you can just refer to that table to implement the modules in the execution stage. So in the next video, I'm going to give you a demo of execution stage. Thank you.